All right, 1.6, the design of experiments. So we've got 5 objectives, so let's get started on those. So objective 1, describe the characteristics of an experiment. So first of all, an experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables or factors that it has on a response variable. Any combination of the values of the factors is called a treatment. Now we have within an experiment, we have the experimental unit or subject. That's usually a person, but we can have objects or another well-defined item in which the treatment is going to be applied. We have a control group, and that serves as a baseline treatment to compare our other treatments. We also have placebo, and this is typically an innocuous medication such as a sugar tablet. It's going to look, taste, and smell like the experimental medication, but it's actually not going to do anything to the patient. And so we will use that from time to time. Blinding, this refers to non-disclosure of a treatment in an experimental in an experiment. So we have a couple of different types of blinding. We have a single blind, and that's where the person or thing that is receiving the treatment doesn't know whether it's an actual treatment or a placebo. So they don't know what they're getting, they don't know anything about it, they just know that they're receiving something. In a double blind, that means both the person receiving and the one giving don't know what they have. So the person receiving doesn't know what type of medication or whatever they're doing is happening, and also the person doing the research doesn't know what they're giving. It's all done kind of behind the scenes and set up so that that person can't lead the person doing the experiment in a certain direction. All right, so let's look at an example here. Lipitor, this is a drug for cholesterol made by Pfizer, and they want to look at the effects of Lipitor on cardiovascular disease. And this was assessed on 2,838 subjects, ages 40 to 75, with type 2 diabetes. And they don't have a prior history of cardiovascular disease. In this placebo-controlled double-blind experiment, so we both have a placebo and a double-blind, subjects are randomly selected to either the Lipitor 10 milligrams or the placebo and followed for 4 years. Okay, and then the response variable was the occurrence of any major cardiovascular event. Okay, now Lipitor significantly reduced the rate of major cardiovascular event. There were 61 deaths in the Lipitor group and 82 in the placebo group. So the deaths are pretty close, but the events was much. We see there are 83 events in Lipitor compared to 127 events in the placebo. It might not have caused death, but there was an event that did happen. All right, so what does it mean for the experiment to be placebo-controlled? So it has a medication going that looks very similar to the other, but it actually doesn't do anything. So that's our baseline to compare to in the placebo, the group that has the placebo. And then what does it mean for it to be double-blind? Well, double-blind again means that the people taking the pills don't know whether they're getting the placebo or the Lipitor, and also the one giving the pills doesn't know if they're giving Lipitor or the placebo. That's all figured out, again, behind the scenes. What is the population for which this study applies, and what is the sample? So our population are any individuals 40 to 75 with type 2 diabetes without a prior history of cardiovascular disease. So pretty specific there on those things. But it can be anybody at that age, doesn't matter where they're from, just any of those people. And then the sample was the actual 2,838 subjects in the study. The treatments were 10 milligrams of Lipitor or a placebo. And then the response variable is whether the subject had any major cardiovascular event, such as stroke or not, and this is qualitative. They had a stroke, they had a heart attack, any of those types of different things with those. Okay. All right, objective 2 here, we want to explain the steps in designing an experiment. All right, so to design an experiment means to describe the overall plan in conducting the experiment. All right, step 1, identify the problem to be solved. So this is a statement of the problem, should be explicit as possible, should provide the experimenter with direction, what to do. Statement should also identify the response variable in the population study. Okay, this is also usually known as the claim. Step 2, determine the factors that affect the response variable. So the factors are usually identified by an expert, and so they may ask, what things affect the value of the response variable and so forth with those things. Step 3, determine the number of experimental units. As a general rule, choose as many as you can. The more people or more things that you can do your experiment on, the better data you're going to get with those. And so we always look for that. We want as many as we can possibly get into that to fall within our time frames and all of those things with those. Okay. Now later on, we'll look at what we need and how to determine those sample sizes, kind of a minimum amount, but we always want to get as many as possible. Step 4, determine the level of each factor. So there are 2 ways to deal with factors. It's either to control the factors or to randomize the level there. In order to control, there are 2 ways to control the factors. We set the level at one value throughout the experiment. Okay. And then 2, we can set the level at set the factor at various levels. Okay. Randomize. This means that we randomly assign experimental units to treatment groups. This can be difficult, but not impossible, to identify all the factors in the experiment. Randomly assigning experimental groups mutes the effects of variation attribute. Okay. Step 5, we need to actually conduct the experiment. We want to do replication. Replication occurs when each treatment is applied to more than one experimental unit. So the more times we can replicate things, the better it is. Okay. And then collect and process that data. Measure the value of the response variable for each replication. Finally, step 6, we want to test the claim, and this is the subject of inferential statistics. And again, that's the process which generalizations about a population are made on the basis of the results from a sample. Okay. All right, completely randomized design. A completely randomized design is one in which each experimental unit is randomly assigned to a treatment. So we don't know, they're just thrown in there. Usually computer generated to figure out where they go. We're not getting to pick what gets to go where. All right, so an example here, a farmer wishes to determine the optimal level of a new fertilizer on a soybean crop, and so we want to design an experiment to help them. All right, so step 1, we need to identify, the farmer wants to identify the optimal level. Okay, so we define optimal as the level maximizes yield. We want the best yield of soybean. And so the response variable will be the crop yield. Step 2, some factors that affect it is going to be precipitation, meaning rain, the amount of sunlight, the method of tilling the soil, type of soil, plant, and temperature. In this experiment, we're going to do 60 soybean plants. Okay. Now list the factors and their levels. Okay, so fertilizer. This factor will be controlled and set at all 3 levels. All right, so we're going to look at 3 different levels here of fertilizer and see what's happening with them, which one's going to give us the best yield. All right, so we predetermined that treatment A was going to get no fertilizer, treatment B is going to get 2 teaspoons every 2 weeks, and C is going to get 4 teaspoons of fertilizer every 2 weeks. Now the other thing is precipitation. Rainfall cannot be controlled, but the amount of watering can be. So each plant will receive the same amount of precipitation. Sunlight, this is also an uncontrollable factor, but it'll be roughly the same because all the plants are going to be in the same area, so they're going to get the same cloud cover and all of those different types of things. Method of tilling, control this factor by using Roundup Ready method for tilling for each plant. So they're just going to use the same type of tilling for every plant. The type of soil, this can be certain aspects of the soil, such as acidity, can be controlled. We can check that, we can pull the soil up and see how those things are done with that. And if we put it all within a certain area, we're going to assume that the soil conditions are pretty equivalent. Now, each plant, there may be a variation from plant to plant, so being random is going to help us on that. And then temperature, again, this is uncontrollable, but it's kind of like the sunlight. They're all going to be very closely located, so they're all going to end up with a very close temperature. Step 5 here, we're going to randomly assign each plant to a treatment group. So we're going to number all of our plants and generate 20 numbers out of it. So we'll be using a computer here probably to do this with those. And so those first 20 numbers that get generated, we're going to put in treatment A. So then we're going to redo everything with the plants left. So we've got 40 plants there. We're going to generate 20 numbers out of those 40, and that's going to be our treatment B. And then the last 20 that are left get treatment C. And then we're going to follow all of our scheduling that we prescribed. All right, and then at the end of the season, we'll determine the crop yield. Okay, so again, for a random assignment, we have group 1, we get 20 plants, group 2, 20 plants, group 3, 20 plants, and they all get their individual treatments on those types of things. Then we compare the yield and make any inferences. All right, match pairs design. A match pairs design is an experimental design in which the treatment units are paired up. The pairs are matched so that they are somehow related. That is, it could be the same person before and after treatment, twins, husband and wife, people in the same location, so forth. There are only 2 levels of treatment in a matched pairs design. All right, so an example of that, we have an educational psychologist who wants to determine whether listening to music has an effect on a student's ability to learn. All right, so match students according to IQ and gender. So for example, 2 female students with IQs in the 110 to 115 range. For each pair of students, flip a coin to determine which student is assigned the treatment of a quiet room or a room with music in the background. Okay. All right, so each student will be given a statistics textbook and asked to study. After 2 hours, the students will enter a testing center, take a short quiz on the material, compute the difference. Okay, so notice there they only have those couple of things happening matched up so that they're closely related on those pieces. So we matched students according to their gender and IQ, randomly assign their treatment, administer the treatment, and then compute the differences on the exam. Randomized block design. Grouping together similar experimental units, also known as homogeneous, but that means very similar, then randomly assigning the experimental units within each group to a treatment is called blocking. Each group of homogeneous individuals is called a block. A randomized block design is used when the experimental units are divided into these blocks. Within each block, the experimental units are randomly assigned to treatments. All right, so again, going back to the farmer, we have the soybean plants. We're actually 2 different varieties. We have the Kimgrow and the Pioneer soybean. So we have 30 of each of those. And the 2 varieties have different yields. So now we want to look at an experiment for them. So in a randomized block design, we would divide 60 plants into 2 blocks, the 30 Chem Grow and the 30 Pioneer. So we have the block of Chem Grow and the block of Pioneer. Now we break it down like we did earlier, 10 plants into treatment A, 10 into B, 10 into C with those things, and see how they will yield. All right, and so the logic is each block contains plants of the same variety, so we're comparing plant to plant. As you've probably heard, apples to apples instead of apples to oranges with those things, so that we can then look at those and how do they affect those things. All right, so here's how this would go. We would break things into block 1, the Chem Grow and the Pioneer, and then we would break those things down into our treatments A, B, and C and compare the yields. And we could probably even go further and compare the yields of each block to each other as well. All right, so those are the things that you're going to need there for 1.6, looking at those definitions and so forth.